Welcome to qnawire.
Okay, in this problem, we are given the Maxwell distribution for speeds in an ideal gas at a certain temperature. And we were asked to prove two different things about this distribution. Specifically, in part A, if we integrate this distribution over all speeds, we end up with the total number of particles in the gas, big N, which should be given. And also this second integral, if we integrate v squared over n times the distribution, f sub v, over all the speeds, we get 3 kt over m. So these are two properties that we need to prove. So this is essentially just a difficult integration. So let's jump into it. So to start, we need to make use of an integral property. We can get this from a table of integrals. It'll be useful to us. And that's that if we integrate from 0 to infinity, something that looks like x squared over times e to the ax squared dx. This is a type of Gaussian integral. The result for that is root pi over 16a cubed, where a is some arbitrary constant that is in the exponential. So we're going to apply this when doing this integral. So plugging in the actual Maxwell distribution, we have 4 pi big N times all this stuff, which are just constants, m 2 pi kt, 3 halves, rather, v squared, e to the 1/2, mv squared, kt, dv. Okay, so we can pull all these constants out to start. Let's say that x, doing just a change of variable, we'll call this root mv squared for 2 kt. Therefore, x squared is just mv squared over 2 kt. We're just setting up this integral to look a lot more like the table. We can say v squared is 2 kt over m x squared. Thus, v is root 2 kt over m times x. We're going to use this new variable x just to get this in the right form as the table. So it also must be the case that our little infinitesimal element dv is root 2 kt over m. Just doing a derivative times dx, of course. Okay, so now we can replace everything in the integral, get it in a more familiar form. Our integral is now still integrating from 0 to infinity. It's 4 pi n over m 2 pi kt. So we just have all these same constants, nothing interesting there. But now there is some new stuff. Replacing v with our new demi-variable x, we have this new constant that appears, times x squared, e to the negative x squared, and all this is multiplied by 2 kt over m. This is to the 1/2, it's a square root, dx. Okay, so we replaced dv, which is this. We replaced the v squared, which was here. Okay, and we replaced the v squared here as well. Okay, so now it looks a lot more like the table, so we can actually do the integral. The integral will come out to be, I'll combine the constants. Combining all the constants, we have 4 pi n times m over 2 pi kt to the 3 halves times 2 kt over m. I'm just pulling all of this out of the integral, as we should. 2 kt over m to the 1/2. the integral that we actually have to do is real simple now. It's just x squared e to the negative x squared, which is the Gaussian integral given in the table on the previous page. Completing the integral, we have 4 pi n times 1 over pi to 3 halves times root pi over 4, which, doing just simplifying, will be n. So it was a fairly difficult integral. We had to get it into an alternate form that we can actually use, but there it is. When you integrate over all the velocities of the Maxwell distribution, you get all of the particles, which is what we would expect to see. So let's look at part B. We're going to do a lot of the same things. The integral that we're trying to accomplish now, we're integrating from 0 to infinity as before, but now it's v squared times the Maxwell distribution, f of v, dv, which is the same thing as this, 4 pi n. These are the same constants as before, m over 2 pi kt to 3 halves, v to the 4 now, not v squared, e to the 1/2, mv squared over kt times the differential. So that's the integral to do. We're going to do very the same exact substitutions. X is going to be root mv squared over 2kt. We can once again say that v is root 2kt over m over x times x. Thus, dv is root 2kt over m dx. Doing as we did before with all the substitutions, the integral will be 4 pi n m over 2 pi kt to 3 halves times 4k squared t squared over m x to the 4 e to the negative x squared and 2kt over m to the 1/2 dx. So we can pull all these constants out as before, do the integral using the table, and we'll end up with the desired n. Actually, let's do it in one more step. Let's just show it. One more step. We pull all these constants out. The integral to do is x to the 4 e to the x squared dx. Which will give us a desired n 3kt over m from the table. Thus, if we were to do the same integral, if we were to do 1 over n, integral 0 to infinity of the exact same thing, we would have this result divided by n, which would give us 3kt over m, which is the desired result. So this problem is difficult because you're using some tricky integrals, some Gaussian integrals, and you have to get it in the right form. But aside from that, it all follows.